Dear colleagues, it's a great pleasure to have you at this seminar in the series of the Department of Epidemiology of the Harvard School of Public Health. This is a very special seminar. It's a works in progress seminar, and one of our great postdocs is delivering this particular seminar, namely Dr. Jing Li. Dr. Li is, as I said, a postdoctoral fellow in the causal lab of the Department of Epidemiology, and she is mentored by Dr. Miguel Hernan, who you see most likely now as well. Dr. Li has a bachelor degree from Wuhan University in China, has a PhD in computer science from Beijing University, and was advised by Professor Yuqiu Wang in the School of Computer Science, and then 3 years ago came to the Harvard School of Public Health to work in the causal lab. And it's wonderful, Dr. Li, to have you, not only in this seminar, but overall in our department. You work on focusing in your work on combining causal inference with machine learning methods to better understand the effects of treatments and intervention in complex longitudinal settings. And you focus particularly now, and we will hear about that in this seminar, on G-formula methods. Your title is Deep Learning-Based Estimator for the Non-Iterative Conditional Expectation, the NICE G-formula. It's a great pleasure to give you the floor. Dr. Jing Li.
Thank you, Dr. Hoffman. Thank you for the introduction. And thanks to everyone for joining this seminar today. Today, I'll be sharing our recent work on advancing the G-formula method. Now I will start sharing my screen. I'll be sharing our latest work on deep learning-based estimator for the non-iterative conditional expectation G-formula. So I'll introduce following this outline. First, I will introduce the conventional parametric G-formula estimator, and then how we extend the parametric estimator into a neural network-based G-formula estimator. Specifically, we incorporate the recurrent neural network, LSTM, into the next version of the G-formula to build an LSTM-based G-formula estimator. And for both estimators, we not only care about their point estimates, but also their uncertainty. So I will also introduce how we quantify the uncertainty of both estimators, and in particular, introduce a new sample splitting and cross-fitting strategy for the LSTM-based estimator. Next, I will introduce our study design in a longitudinal setting, where we evaluate the performance of both estimators. The final part is discussion, which is also our QA session. If anyone has any questions, feel free to ask during the QA session. Now let's start with the NICE G-formula based on parametric models. Here, this formula shows the NICE version of the G-formula. It expresses the causal quantity of counterfactual mean outcome in terms of a joint distribution of all time-varying covariates, treatment, and the outcome over time. So if we want to estimate the G-formula, we need to estimate such a joint distribution. It can be factorized into separate conditional distributions, which contain the conditional distribution for each covariate, conditional on its past history and treatment history, and also the conditional distribution for the outcome, conditional on the covariates and treatment history. When using parametric models, we fit a parametric model to estimate the conditional distribution for each cover rate, and then fit a parametric model to estimate the conditional distribution for the outcome. Once we have fitted these parametric models, we can then apply Monte Carlo simulation to approximate the sum or integral in the G-formula. During the Monte Carlo simulation, for each simulated individual, the covariates and the outcome are generated using the fitted parametric models. And for treatment variable, its values are generated following an intervention or treatment strategy. And then we can compute the counterfactual outcome of interest. So this is how the parametric G-formula works. Now we extend the nice G-formula based on LSTM models. Here, instead of fitting separate parametric models for each covariate's conditional distribution, we use one single LSTM model to estimate the joint distribution of all time-varying covariates, and then fit another LSTM model to estimate the conditional distribution for the outcome. And for both LSTM models, we need to determine their hyperparameters. And we do this by performing hyperparameter tuning. Once we have obtained these best hyperparameters, we can then train an LSTM model to estimate the joint conditional distribution for all the time-varying covariates, and then train another LSTM model to estimate the conditional distribution for the outcome. And finally, same as parametric G-formula, we apply Monte Carlo simulation to approximate the sum or integral in the G-formula. During the Monte Carlo simulation, the trained LSTM models are used to generate the covariates and the outcome for each simulated individual. And then we can compute the counterfactual outcome with these simulated trajectories. Here, this figure shows the overview of the LSTM-based estimator. So we first fit a joint covariate model to predict the covariates at each time point, and then fit an outcome model to predict the outcome at each time point. Then during the Monte Carlo simulation, the covariates are generated by sampling from the estimated conditional distribution. And for the treatment variable, their values are replaced by their intervened values following an intervention or treatment strategy. And at each time point, the probability of the outcome is predicted using the outcome model. Here we focus on survival outcomes, so we can compute the counterfactual risk using the previous predicted hazard probabilities. And the method can also be extended to non-survival outcomes similarly. Here, this figure shows the model architecture for the covariate LSTM model in the nice G-formula. At each time point t, there is an LSTM cell that takes the history of covariates and treatment as the input. It maps the history into a hidden representation, which is followed by a head layer. The head layer is an MLP, which consists of multiple linear layers, followed by nonlinear activation functions. At each time point, the covariates are predicted using the neural network. When the covariate is continuous, the neural network will output the estimated mean of that cover rate at each time point. Its standard deviation is estimated using the root mean squared error of the LST model. When the cover rate is binary, the neural network will output a probability between 0 and 1. When the cover rate is categorical, the neural network will output the predicted probability for each category. Then in the following Monte Carlo simulation, the cover rates are sampled from the corresponding estimated conditional distributions. And this figure shows the model architecture for the outcome LSTM model in the G formula. Similarly, at each time point t, there is an LSTM cell that takes the history of cover rate and treatment as input. It is followed by a head layer, which is also an MLP. It will output the predicted probability of the outcome at each time point. And then during the Monte Carlo simulation, the LSTM model will take the simulated history of cover rates and treatment at the input, and then predict the output, predict the probability of the outcome. So now we know the model architectures for both LSTM models. One question is, how do we choose a good model architecture? If we want to have a good LSTM model, we need to select appropriate hyperparameters for the LSTM model. Here, these hyperparameters contain architecture-related hyperparameters and training-related hyperparameters. The architecture-related hyperparameters include the number of recurrent layers in the LSTM, the hidden size of the LSTM cell. They determine the architecture of the LSTM model. And then the training-related hyperparameters include learning rate, batch size, dropout probability, and weight decay. They determine the training performance of the LSTM model. And we select the best hyperparameter configuration by performing hyperparameter optimization or hyperparameter tuning. Specifically, we evaluate a set of candidate hyperparameter configurations and then select the one that achieves the best performance on a holdout validation dataset. Once we have obtained the best hyperparameters, we can train the LSTM model for the following Monte Carlo simulation. So this is how the LSTM-based G-formula works. Now I will introduce our sample splitting and cross-fitting strategy for the uncertainty quantification of the LSTM-based estimator. The basic idea is to preserve the independence between model selection and G-formula estimation to make valid inference. When we don't do sample splitting, we use the same observational data for both hyperparameter tuning and G-formula estimation. When we do sample splitting, we use separate data for hyperparameter tuning and G-formula estimation. In the deep model selection, we select the best LSTM model from a set of candidate models. And then in the G-formula estimation, we train that LSTM model on 80% of their data, and then validate the model on the remaining 20% of their data. And then in the Monte Carlo simulation, we use the trained LSTM model to simulate the trajectories of all the simulated individuals. And in sample splitting, we first split the observed data into two halves data A and data B. On data A, we perform hyperparameter tuning to obtain the best hyperparameter set. And then on data B, we perform G-formular estimation to get the point estimate of the risk. We also apply cross-fitting to make full use of the observed data. So on data B, we perform hyperparameter tuning to get the best hyperparameter set. And then on data A, we perform G-formular estimation to get the point estimate of the risk. The final risk estimate is the average of the point estimates obtained from two separate data splits. The way how we construct the confidence interval is that first we apply bootstrapping on data A to obtain the point estimates on each bootstrap sample, and then calculate the standard error with these estimates. And then on data B, we also perform bootstrapping to get the point estimates on each bootstrap sample, and then calculate the standard error. The final standard error is combined with two separate standard errors that are obtained from data A and data B. Then we construct the lower bound and upper bound for the risk estimate with normal approximation. So far is our methodology part. Next, I will introduce our study design. And I will start with the motivating example, which is based on a study on the effect of integrase inhibitor use and cardiovascular events in people with HIV. We simulate the HIV data with survival outcome and without loss to follow-up and without competing events. For simplicity, we simulated the HIV data under a simple time dependency scenario where all the coverage and treatment at each time point depend only on their values at previous time point. Here, this deck shows the data generation process of the simulated HIV data. A represents the time-varying binary treatment variable. 1 means receiving HIV treatment with an INSTI. 0 means not receiving. L0 represents the baseline coverage, which include age, sex, and smoking. LK represents the time-varying coverage, which include the binary BMI variable and 2 continuous coverages, CD4 cell count, and the HIV RNA viral load. YK represents the survival outcome, which is a cardiovascular event. U is the unmeasured confounder variable. In the data generation process, the time-varying coverages are affected by the unmeasured confounder U and the baseline coverage and its past histories. The treatment variable is affected by the baseline coverage and the time-varying coverage. And finally, the outcome is affected by the unmeasured confounder U and all coverage and also the treatments. Here, this is the setting in our analysis. We first simulated the HIV data with two sizes. One is 1,000, another is 10,000, and we generate each individual up to 10 time points. In bootstrapping, we resample from the original data with 300 times. And when calculating the coverage probability, we regenerate the original data following the same data generation process with 1,000 times. And for both the parametric and the GFORM and RSTM-based estimators, we estimate the outcome risk at the final time point under the natural course. And we also estimate the bias of both estimators, and also the coverage probability, which is the proportion of times that the estimated confidence interval covers the ground truth risk over 1,000 simulations. Here is how we obtain the ground truth risk. We first generate a dataset with 10 million individuals. Then we calculate the risk at the final time point for each individual. Finally, we average the risks across all the individuals to obtain the ground truth risk, which is close to 0.165. And for the parametric G-formular estimator, we tried 3 model specifications, and we call them model V1, V2, and V3 here. In model V1, the model statement for each cover rate and the outcome is misspecified. That means these models deviate from the true data generation process significantly. And then in model V2, the model statement for each cover rate and the outcome is specified using the terms that are used to generate corresponding variable in the data generation process, and also includes additional interaction terms of the cover rate, as well as the terms of the time variable. So that means compared with model V1, the model V2 is more closer to the true data generation process. And then in model V3, the model statement for each cover rate and the outcome is specified using the terms that are used to generate the variable in the data generation process, and also includes the term of time variable. So compared with model V1 and model V2, the model V3 is closer to the data generation process. And for evaluating the LSTM-based estimator, we tried 2 settings. One is with sample splitting, another is without sample splitting. In the setting with sample splitting, we use half data A for hyperparameter turning, and then half data B for G-formular estimation. Here, when performing hyperparameter turning, we select the best hyperparameter configuration from 50 candidate hyperparameter sets. And in the setting without sample splitting, we use the same full data for both hyperparameter turning and the G-formular estimation. This table shows the quantitative results of both estimators on the 1,000 size data. For the parametric G-formular estimator, we can observe that when we increase the model correctness for the model statement from model V1 to model 3, the bias of the estimator becomes much smaller, and the coverage probability reached to 95% nominal level. And if we look at the estimators with the LSTM model, the one with sample splitting has a bias that is smaller than all the estimators, and the one without sample splitting has a bias that is much smaller than parametric model V1, which is largely misspecified. And if we look at the coverage probabilities, both LSTM estimators achieves to 95% nominal level. And if we look at the standard error of bias on both estimators, we can see that the LSTM-based estimator has a larger standard error than the parametric G-formular estimator. which exhibits higher instability and variability in its estimation. The reason is that compared with parametric model, the LSTM model has a high-dimensional and flexible architecture with many parameters, making it sensitive to random fluctuations, and also makes it has a higher stochasticity in its training process. If we look at the quantitative results on 10,000 size data, similarly, when the parametric model is largely misspecified in model V1, the bias is large, and it has a very low coverage probability with 15%. And when we increase the model correctness in model V2 and V3, whose model statements are more closer to the true data generation process, the bias becomes much smaller, and the coverage reaches to 95% nominal level. And for the two LSTM-based estimators, they have a similar bias that is much smaller than the parametric model V1, which is largely misspecified, and is slightly higher than model V2 and V3, whose model is more closer to the data generation process. And when looking at the coverage probability, the one with sample splitting has a probability that is slightly lower than 95%. And the one without sample splitting has a probability that is slightly higher than 95%. So the one without sample splitting is more conservative than the one with sample splitting. The explanation is that when we don't do sample splitting, we use the same data for both hyperparameter turning and the J-formula estimation. Then the final variability comes not only from the sampling variability, but also from the uncertainty from the hyperparameter turning. So that makes the estimator becomes more conservative than the one with sample splitting. And when comparing the standard error of both LSTM-based estimator and the parametric estimator, again, we observe a higher standard error for the LSTM-based estimator. So that means the LSTM-based estimator has a larger variability than the parametric estimator. Here, these two figures show the coverage on 1,000 simulations for the parametric estimator. And the vertical orange line represents the ground truth risk. The horizontal black and red lines represent the estimated confidence interval on each simulated dataset. And we can see that when using parametric model V1, which is misspecified a lot, on both sample sizes, the parametric estimator has a low coverage, especially on a larger sample size with 10,000 individuals. And when we increase the model correctness in model V2 and model V3, we can see that both coverage probabilities become closer to 95% nominal level on both sample sizes. Here, these two figures show the coverage on 1,000 simulations of the LSTM-based estimator in the setting with sample splitting. On a smaller 1,000 size, the coverage probability is slightly higher than 95%. And on the sample size with 10,000 individuals, the coverage probability is slightly lower than 95%. And in the setting without sample splitting, on both sample sizes, the coverage probability is slightly higher than the 95%, which show that it's a bit more conservative than the one with sample splitting. Based on these results, the conclusion that we can make is that the parametric G-formula estimator can suffer a lot from large model misspecification. And so the bias of the parametric G-formula estimator decreases when their model specifications are more closer to the true data generation mechanism. That means the parametric G-formula estimator generally requires correct specification to achieve accurate estimation and valid coverage. When the data generation process is known and the generation function is easy to model, the parametric G-formula estimator can leverage and benefit a lot from the knowledge of data generation process. When the data generation process is unknown or too complex to model, then the LSTM-based estimator can be an alternative. It can be more robust to model misspecification, since it doesn't require any explicit functional form to estimate the coverage and the outcome. So it can have small bias and also achieve valid coverage that is close to 95 nominal level. Basically, the LSTM-based estimator has a larger standard error than the parametric estimator, because the LSTM model has a high dimensional and flexible architecture with many parameters. So compared with the parametric G-formula estimator, the LSTM estimator has a more complex architecture, which introduces both larger flexibility as well as more variability. Here is our computational environment, which includes both the software environment and also hardware environment. The hardware includes the CPU and multiple NVIDIA GPU types to run both the parametric estimator and the LSTM-based estimators. If we compare the time efficiency for the parametric estimator and the LSTM-based estimator, we can see that the parametric estimator can be much faster than the LSTM-based estimator. The reason is that the LSTM-based estimator has a model training step, which is very time-consuming, especially when there is bootstrapping or large simulations. Currently, we apply parallel training on multiple GPUs for acceleration. And the way how to better optimize the time efficiency of the neural network-based estimator remains a future direction of our work. So the above is all my introduction of our recent work. Thank you for your attention.